Hello, welcome back to Information Storage and Retrieval. So, we are making our way. We've talked about a variety of different ways to think about our terms, how we can define our vocabulary. But now we're going to go a little bit more into an implementation direction today and talk about the kinds of structures, data structures that we might want to use to make our dictionaries useful to computers, right? Given that this is all about building a system that can access our dictionaries and thus our postings and documents, we need to know what exactly are the implications of choosing one data structure over another for actually storing these lists of terms. So let's do a little walkthrough of our systems. We keep elaborating this, right? So, as always, we start a human has an information need, and we know that there's an unstructured information pool out there in the world. So, here comes our information retrieval system, right? Often I have not drawn the delineation here, but remember, like, people will come to your system with a need, like a search engine, and they will input their query, and your system will only really work on what you've pulled out of the unstructured information. So, things like your collection, right? So we can pull down our collection from wherever, however we choose to harvest it, and then we start processing it. We normalize the collection, the strings of text in the collection, we tokenize them, and we start our indexing process. As we recall, indexing is the index produced is a dictionary of terms and the postings associated with each term of the collection of unstructured information available to our system. So then the user comes in and says, I have a query. So we take that query and we normalize it and tokenize it just as we did with the documents. And then we get our terms. Now, here is where our first step of processing the query must be answered. Now, we know logically this is going to be, ultimately, we're going to go in and intersect the lists of postings to get the addresses, the locations of the documents in the collection that the user wants, right? But that very first step, we need to figure out, is this term even present? How do we find the term in the dictionary? Well, that is not a non-trivial question. So the very first step is to figure out if it's in there. And the way we answer this depends heavily on how we choose to implement the index and its dictionary. So remember, we have our set of terms and all of their associated postings, but how exactly do we use them, right? We as humans can look at them, and that's what we've mostly done so far, right? We say, I see that this term has these postings. That's fine for a person, but we're slow. Pardon, pause to clear my throat. We're slow. This isn't for a human to dive in and dig up. We need a system that does this well. So we got to figure out, how are we going to actually store our index components, right? The dictionary and the links to the postings, which are links to documents, right? Because a program needs to access these, and we need to make a decision about how the program will be able to both store and access all this information. So, simple dictionaries, as we've kind of thought of them so far, the terms can just be in a basic list or an array, either way. That just a collection of information that's linear, right? And the simple way to try and search for a term, right? So we've received a query and we're going to say, hey, let's go get the postings for this first term of the query. Well, the simple way is to just run through the list until we find, oh, this term is right here. Great. So, I've written some pseudocode here. So for the term in the dictionary, if the term is the query, go get the postings for it, right? This is a linear process. And as we've said before, we're always trying to do a little better than linear if we can. And, we know the issues, right? If I have 1,000,000 billion terms in my index, running through the entire index one piece at a time every time knocking on every door, so to speak, it's not going to be great. So as we said, best case is, hey, it's the term A. Great, I already got it. Worst case is it's term Z, 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 So it's a lot of terms. We don't want to rely on a simple linear search just because there's so many other possibilities available. So we're going to talk about two of those today. First is search trees, and then hash tables, which incidentally, hash tables are the way we're going to go in our own implementations in this course, just because they are wicked simple. At least the way that we use them is simple. We'll talk about how they work here today. So, search trees. We need to talk about linked structure first before we get into search trees. So, link structures. Here's a kind of a basic primer on some data structures and algorithms type information, but we'll just keep it at the high-ish level, but give you the basics, give you the details. So linked lists you may have heard of, and trees you may have also heard of, rely on the same basic idea, and that is that wherever information lives on the disk, we can connect it using links. So wherever the data is floating around, it doesn't matter so long as we can actually connect the information using memory addresses. So let's talk about memory addresses. All data on your computer, in every computing system, is going to be stored on the disk or in memory, even the faster bit of information. It uses some kind of address system. So there is a binary numerical value physically encoded into your computer that represents some slot of information that you could store there. Every time you define a variable in a system, especially a simple like a numerical variable, this is saying, hey, I'm going to set aside a piece of memory that, again, your programming language hides this from you because you don't need to worry about exact memory addressing. But the idea is that variable now points to a place in memory, so that when I write the number 54 and I assigned it to some variable, that variable will go to memory and say, aha, I found 54. Hope that's making sense. So the idea is that we use an addressing system to keep track of all the data that is stored by a program, by a user, by anyone, right? And if we want information, we can just go to that address and either pull it out or write to it, change it, right? And a little note here on why you're seeing letters in the memory address field. That's because there's a very easy way to convert binary notation into a simpler, more compact form, and that's called hexadecimal. So every hex character in a hex number, it represents 16 possible values as opposed to, say, our normal 10 in digits. Hexadecimal means 6, 10, right? So 16 possible values. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F. So that if the number 0 is in one of these slots, that actually is 0, 0, 0, 0 in binary. And if it's F, that's 1, 1, 1, 1 in binary. Okay, so just so it's clear how the memory addresses are working. Okay, so memory addressing is key to how basic access of data on your computer works. You might ask something like, oh, well, how the heck do I store a whole document there? You don't. You store a link to the document, which is a whole bunch of memory addresses stored somewhere else on the computer. So let's continue with link structure. So in linked structures, linked lists, trees, all these things, every item has a few things. First, it has its own memory address, right? Wherever this actual item lives in memory. It has the data, so the content that we actually want to use, right? So this is all the infrastructure around getting access to a single piece of content. In our case, we think of this in terms of terms, although I will note that terms are typically strings, which are a little more complex than a single number. But you don't have to worry about that. The core concept is the structure that we're talking about, the information lives at some address and it has some data, but it also has a link to the address of something else. So that if in this very short list here, if term A lives at FFE2, but it has a link to its next item at CAD3, well, we go to CAD3, we find term B, and it has a next address, 0057, term C, and so on. So let's look at a longer list. Here we have FFE2, term A, again, CAD3. Well, that links together. The link between these two creates a list. This is no longer just two terms floating in memory, but now they are linked terms. We can link another. Continue linking. We can link and link and link and link and link until we stop linking. Okay, so this is, you might ask, well, Lord, why do we do all this extra effort to make just a linked list when we could just do this with an array and that does them all simply, right? Well, the answer is that links are super flexible, and they're quite powerful. So while the linked list might have this kind of linear structure, and in fact, if you think about this, if I only know where the first term is, I'm not going to be able to, the only way to progress through this list is to go from term A to term B to term C again. So we're just replicating this sort of poorly optimized search pattern. But we can implement a different structure using links that is way faster. Trees. So a tree item, a node, an item in a tree, might have more than one link, right? So you could make it so that this root node up here has a link to data that is smaller than term D, for example, term B, and data that is larger than term D. We're getting into a different kind of structure, aren't we? So the address of child A points down to our smaller term, our lexically smaller, right? B is earlier in the alphabet than D. Whereas child B can point over to F. And then we can separate again. So term B might point down to term A's and C. And term F might point down to E and G. Okay. So now if we want to start a search through this tree, we're going to get through 1, 2, 3, 4, 5, 6, 7 items. Guaranteed, we're going to get to our destination in 2 jumps. I can start at the top at this sort of mid-range term D and say, hey, is my term lexically larger or smaller than this one? And then keep going. Jump down twice and we're done. That's interesting. That is a way that we can kind of cut out the chaff and use this linked structure to optimize our search down to, this would actually be logarithmic time, because we can search, if you continue this pattern, and if every node in this tree has 2 children, well, we're going to double our search breadth with every jump. Double it again, double it again. That's the power of trees. That's why trees are so useful. So how do we use this to implement a dictionary? So again, while a simple dictionary could be stored in a regular old linked list, we would be stuck linear searching just like when we started. So we're going to use trees instead, search trees specifically. So each tree has some head node, as I discussed there. That's where you start your search. And every node links to multiple children. And the branches get more and more specific until you run out of places to search, right? So one structure here is binary trees, and that's what I just displayed to you before. Every node will have 2 children. And again, that means that every branch off of one of the children as we're traversing down the tree cuts the search space in half. That's great. This logarithmic search time, runtime. Let's look at how people typically implement this for lists of words. So here's an index, right? And these are notionally the order of the words, right? But we're going to store them in a tree. How do we store them in a tree? Well, we can build the tree with decision points based on the first letter. Okay, so from the head node, we have letters A through I represented on the top children, and L through Y represented on the bottom children. Keep going, keep splitting the search space. So we would have to run through to make these decisions about where the cut points are a few times, but again, once we build the structure, it's usable. So now the top half of the A through I is going to be A through E, and the lower half will be G through I through S, T through Y, and so on, until we reach the nodes, right? The actual terms in the dictionary. So now, if I want to search for here, H-E-R-E, well, I can lop off the first letter and say, hey, let's look through, where does this fall? Well, we're going to take the first branch up, right? H is right before I. Great. I'm going to take this next turn. I still have the ability to use this letter to figure things out, so I'm going to keep going. G through I, E, F, G, H, I. Okay, great. G through Ha. See, now we've had this decision point where H is no longer differentiates our terms. We had to go to the second letter. So that's what we're going to find out here. We got to look at H-E. Okay, so here, H-E. Great. We can take the bottom branch, and then finally, oh, we've got it. That's the one. H-E-R-E. We found a match. Okay. The reason you do this, remember, the reason anyone would do this, and not just leave this in a big old list, is to cut down on the search time, right? If we had 100 million terms in our dictionary, we would want a better way to reach the end to find the terms that exist in the dictionary without having to just run linearly through the list over and over. So that's how we use binary trees. The search consists of navigating through the tree's branches to find out, hey, where is this term and where can I get its postings from? It also lets us figure out if the term is not there quite quickly. So the search space is cut in half at every step with this binary tree structure, allowing us to cut down on, say we had 10 million terms, right? That would be 5 million steps on average, because it could be best case, it could be worst case, but on average, 5 million steps to find each term. Versus if we do this log-based transformation, the idea of using a binary tree to achieve the same thing, then we get to do every term in 23 and a quarter steps on average. That's great. That's a massive speed up. Now, binary trees also rely on perfect balance to function. So if we need to add new items, what happens? The issue becomes, what happens if we add 1,000 words with the letter Y in them? That's going to be a lot of letters just kind of tacked onto the bottom of this tree. We would have to restructure and rebalance the tree quite often to make use of it. Now, this isn't to suggest that no one uses binary trees in search. In fact, they allow for a few unique things, but we'll cover those as needed. So adding things onto the end of the tree makes it more and more linear. You'd have to rebuild the tree over and over. Again, a very costly operation to compare every item and find out all of the cutoff points again and again. So Not a big deal if you're just going to build an index once, or relatively infrequently, but still, this is the cost. This is the issue with doing everything in a binary tree. Another option aside from binary trees is B trees. These are a little different. So B trees allow you to have as many nodes as you want under each child. Not infinite, right? Not as many as you want, I suppose. But a better option is, a better way to think of it is, you can have, depending on what the structures are in your language, for example, it makes it easier to plop a few more under each node, and then you add a little bit more linear search per node, but it still makes it so that the rest of your tree remains flexible. So it makes it so that you can insert more information at each step, and you might have to linearly search through it, but this also makes it easier to add things to a B tree because it's not locked into this binary choice on every node. Still, trees are useful. They let you really optimize search time to figure out where each term is in your dictionary, just so you can even get at the postings in the first place. But it's a little finicky. It's pretty straightforward to implement it yourself, but it requires you doing that and testing it and making sure it works well. So a lot of languages already have tree packages available, structures that are available for you to use outright. So search trees, binary trees and B trees, they're flexible. They're quite nice. They run in this logarithmic time, way better than linear, as I showed you. 23 versus 5 million. That's pretty important. And they also, like I said, they enable some unique things. We'll talk about these more next time, but things like partial matching. You could see how maybe if I wanted to find words that begin with ABC, well, I can run to the ABC point of the tree and then say, hey, give me all of the things under here. I'll run a search on any of those. That gets into the idea of wildcards. Again, we'll talk about that next time around. So that's trees. This is one way you can build your dictionary to be very easily searchable. Another way is to use hash tables. So let's talk about hash tables. As with the trees, I need to give you a little primer on arrays first. Some great things about the noble, simple array, right? If you know the address of the item you want, you get it in one step. That's constant time. That's exciting. So if I want the item at address 1 in this array, index 1, I get it instantly. I don't have to go looking. I know where it is because I know what index I'm after. So in array world again, so memory addresses. So your system will keep track of, when you create an array, your system will keep track of the first address of the array, right? And then the index of the array has to do with the offset. This is why, this is subtle point, this is why indexes start at array value 0, right? At index value 0, because there's no offset. I'm just give me the first item. Give me the item that is at this part, right? So if you ever wondered why everything starts at 0 in computing, it's because of this. So if you know the offset and you know the first address, then you just go to it. You don't have to search, right? We can just immediately pull out the item that we want at that value. You do have to do one operation. You have to add the offset to the first address, but that's fine. So this works. This allows us to go straight to a destination in an array, and we don't have to knock on every door in the neighborhood because we know where the address that we want is. When we know where our friends live, we don't have to go looking around for them. But our terms aren't integers, and we can't just use this, that because they're not just stored in simple linear ascending order as integers. And also, remember, we are searching, right? We don't know where our friends live. If our list of terms is a million things long, and we're trying to find a particular term, I don't know exactly what address it's at. It may have moved around. It may not be. I don't know where that term is in the millionth spot, right? So if we leave our terms in arrays, once again, we're back to linear search. We have to look through each one. We have to knock on every door in the neighborhood. Unless we can start using hash functions. A hash function will take any given string and attempt to convert it into a unique integer. So a hash table creates an array that uses the hash function's output of an integer as its index. So it turns all of our terms into integers. So now when we go to talk to the array, to the list, to the dictionary that might be stored in through a hash function, we're speaking the same language. If I give it a term and it's able to convert that term into an index, well, where's the search? That's the point. There is no search. Using a hash function, we can remove the entire search through the index, through the dictionary of terms. So using arrays and hash functions, we create a structure that instead of using, indexing into a specific position of an array, we can create a list of keys, which are strings. So we can get direct access to the data, in this case, our postings. As long as I give it the same key, it'll go find it, and it will do it in constant time. Mostly constant time. Got to give, there's no magic in computing. We have to pay the price somewhere. But it's great because it looks and behaves kind of exactly like the inverted index that we want, right? So instead of trying to search through the array, we can just give it the address, the key, dog, and get the postings in an instant, in a single step. So similar to the way that we were using the index originally, as I said, we can only use the index, the array indexing, if we know what index our preferred item lives at. But now we do know where our preferred item lives at because we know our string is cat. That's the key into this structure. And we get cat. So this is why we will be using hash tables. They're quite efficient and they're conceptually pretty simple. It's the idea of just, hey, build me a structure and I'm going to give you words, terms, and you're going to give me whatever the data is, in this case, postings. That's exactly what we need. Now, why might you not use hash tables at scale? And why do we even talk about search trees, etc.? And the answer is hash collisions. So, hash functions try their best to convert a string into a unique value, into a unique numerical integer value. But they are doing something like multiplying the character values of all of the items in the string by a certain amount, dividing, shifting, doing all this fancy stuff. And unfortunately, you can take two terms that seem completely unrelated, and just because of the way the hash function works, it will accidentally store, you will collide, right? So John Smith and Sandra D might be indexing into the same spot in memory, the same spot behind the scenes. That's fine, because the system, any good hash table that you use, in fact, every one of them that exists, it'll just store both items, right? It's okay. We don't need to worry about it. I'll just have both items, and then I'll do a quick check on, hey, what was the key you used? Let me figure out which box to pull out for you. It's a little inefficient, right? And collisions are, in a technical sense, infrequent. But as always, if we're scaling up to millions of documents, millions of terms, millions of things and things and things, as the terms grow, the number of hash collisions start rising, and you will lose efficiency. And it's possible you end up with this kind of scattered, somehow a lot of your terms end up colliding. And now everything ends up, you're pushing back towards linear search. It's still powerful, but, you know, and as we talked about before, we had byword indexes are quite large, maybe different gram sizes. Say I have 10 different gram sizes as we're chopping up words into these specific things. But this is not a major concern, and that's why we will use it for sure. But this is also why it's not the only thing you will see in the search world. So, when it works, it's lightning fast. One-step dictionary access. That's awesome. We have cut out our concerns about one particular chunk of our information retrieval process. And it's also super convenient. You know, modern hashing, every language has hashing available to it. In the language we'll be using, JavaScript, every object you've ever seen in JavaScript is also a hash table. You know, it has a property name, right? And then some value associated with that property name. That works. So these are built right in. So that an index in JavaScript ends up being a list, one big object where all of the keys are our terms and all the values within that are addressed by those keys are the lists of postings, the IDs, right? So the great thing about hash tables is that they're fast, they're easy to understand, they're intuitive to use, more so than most things. You'll see as we toy with them. They're a great option, especially for smaller scale search systems, and even for larger scale ones, they're quite good. But remember, limitations. Scaling has some issues. Too many terms colliding can cause a lot of overlap and end up with a lot of inefficient sort of linear search if you get too many collisions on a single point in your hash table. But again, in modern computing, we're not super worried about that. Systems are fast enough, the solutions are elegant enough that we can just use them. Another limitation, so I talked about how you could do partial matching with the trees. This is still whole term matching. So the hash function can't really pull out, give me the first three letters of. So some of the work, some of the tricks we'll talk about next time with tolerant input, they don't work so well directly here. But we'll also look at some ways around that. So that's the idea. So dictionary structures, hash tables let us use these whole terms as keys instead of index addressing into our dictionary with this beautiful, mostly constant access time, constant perhaps with an asterisk access time. Which again, I cannot stress enough. If you have 10 million items and you can always get the contents of one of those items in a single step, that's fantastic. That's optimum. Whereas search trees are going to use this branching comparison structure that can do some neat things like return partial matching, and they'll run in log time, which is good because it doesn't matter. You know, there's no idea of collisions in search trees, especially if we're using a careful one, a carefully constructed one. So search trees will always give you log runtime, and they enable some other interesting little tricks. So both are useful. Both are implemented kind of everywhere that you might find them, but for different purposes and in different ways. I lean towards the hash tables, of course, but search trees give some cool features. So next time we'll talk about some tolerant input. The idea of using how to implement wildcards, some ideas for spelling correction, and phonetic correction, how to correct phonetic. So next time we'll start talking about tolerant input and some ways to use these structures that we talked about here to accept perhaps imperfect input from the user and still attempt to make sense of it. All right. Final thought. Think of one way you keep things organized in your life. Is it more like a hierarchical tree or more like an address system? All right, take care.